Greetings. Egyptian arithmetic. Egyptians did a really good job with whole number arithmetic. Negative numbers don't exist yet. Decimals are not going to exist until the 1700s for all practical purposes. So the question is, how do you represent pieces parts? Things that aren't a full whole. Well, the answer is simple. You have to be able to represent them using fractions. And I can hear the collective groan of my class as they watch this video. You're thinking to yourself, oh dear God, why? You only think in terms of decimal numbers because you've had a calculator in your hand, probably long before you should have had one. And therefore you think everything should be expressed using these decimal numbers. But for most of humanity's time on this planet, we have not done that. We have represented pieces parts by fractions. And so did the Egyptians. The problem with the Egyptians, and not really a problem, but a way of thinking though, was interesting. The Egyptians did not see fractions the way we do. They viewed things as unit fractions. And I'm going to explain what a unit fraction is compared to our fractions. A modern fraction, I can simply say I have 3 parts out of 4, and everybody hopefully understands this. You may even be able to conjure up a mental image of a pie shape and what 3 pieces out of 4 would look like. The Egyptians did not have the ability to represent 3/4 as a single fraction. They had to use these things called unit fractions, which meant that each fraction must be represented with only a 1 in the numerator. And so the question is, can you find a series of fractions that will add up to 3/4? And for this example, it's not very hard. 1/2 plus 1/4 is 3/4. And so an Egyptian would never dare say 3/4. They would say 1/2 plus 1/4. And the person that receives that information would intelligently know how to interpret this. And I'm sure they did view it as 3/4, but they expressed it this way in writing, using unit fractions. Now, this leads to some interesting problems. What do you do and how do you find these unit fractions when you know in your head you've got something else happening? Let's take, for example, I want to represent 5/12. And by the way, the Egyptians would not have said 1/12 plus 1/12 plus 1/12 plus 1/12 plus 1/12. That's not being a good Egyptian. So we got to figure out what to do here. Now, we can go through trial and error and see what we can do. And in this case, I can very quickly say, hey, 4/12 plus 1/12 is tickety-boo good. And I picked 4 out of all of the numbers because 4/12 simplifies to 1/3 plus 1/12. And lo and behold, I have the unit fraction decomposition of 5/12. So it's not hard to do this for some fractions. Now, the Egyptians did something, and by the time you get to this video, hopefully you've read your text, and you will understand that in one of the papyri that we now have of Egyptian mathematics, they actually would build an entire table of fractions of the form 2 over n, where n is somewhere between 2 and 100. And they wrote out a table. Now, the problem with this is you'd have to have a table for 3 over n, 4 over n, and 5 over n, and whatever possible fraction you can have, you would need to build a different set of tables unless you can come up with a mathematical operation that allows you to do this type of decomposition without having to have this table in front of you. The table is basically like a multiplication table. Hand it to a third grader so they can do their homework problems. I need to be able to figure the tables out though. And we do have several methodologies. One of them was not necessarily used by the Egyptians, but comes along much later in Western European history, and it comes at the time of the Great Awakening mathematically. The mathematical Renaissance will start almost 200 years before what's called the Italian Renaissance. And the mathematician that sparks off the mathematical Renaissance is a fellow by the name of Leonardo da Pisa. You've probably never heard of him, although he's extremely famous, because he never put his own name on any of his homeworks. He used a fictitious name, a nom de plume as it were. We know him as Fibonacci. And Fibonacci said, let's see if we can sort this out. And Fibonacci said, give me a fraction of the form a over b. And I'm going to give you a methodology for trying to figure out how to write it as a group of unit fractions. So with a over b, and he says we're going to let it be more than 1 over n sub 1, and it's going to be less than 1 over n sub 1 minus 1. Now, first time you look at this, you may think to yourself, he's got it backwards. Because you know n minus 1 is less than n, so therefore, how can it be more than? But remember, these are in the denominators, not the numerators. So basically what I'm saying is this. Let's put some numbers up here so we can solidify this. I'm going to let n1 be equal to 3. So 1/3 is going to be less than or equal to some fraction, which is going to be less than or equal to 1 over 3 minus 1 is 2. And yes, a half is more than a third. The question is going to be what fractions fall in between here and how does this methodology help me? And we're going to basically be given the a and the b. We're going to be picking the values of n. And by picking these values of n, we're going to see how to solve certain problems. So, I can fill this board up doing calculations. I'm actually going to do exactly that. So, with the magic of editing video, I'm about to clear up some space. And we're back. We've got clean space. And I want to be able to express 17/20 as a sum of unit fractions. Now, this is a very interesting methodology. It's found in your text about section 2.3, if I'm not mistaken. Let me double check. 2.2, it's called the Fibonacci method. And so the first thing we need to do is pick n an element of 2, 3, 4, 5, 6, 7, etc. And we want to pick the largest, or actually the smallest value of n that we can work with. So we want 1 over this pick is less than or equal to 17 over 20, less than 1 over the pick minus 1. And so I'm going to try 2. Does 2 work? And yes, 2 does. 1/2 is less than 1, and 17/20 is bound between the two of them. Now, this is what you do with the Fibonacci method. Fibonacci method says, hey, once you pick your first n, we're going to take 17/20 and we're going to subtract off of it 1 over n, which in this case is 1/2. So I'm going to get a common denominator of 20. And I now have an answer of 7/20. This is basically saying this is how much I have left over that I don't know what to do with. Now, with 7/20, we're going to do the same thing we just did. We're going to go back to our numbers and ask ourselves, 7 over 20 is going to be less than 1 over n minus 1 and greater than 1 over some value of n. Now we know we've used 2. So now go to 3. Well, 1/3 is less than 7/20, I'm pretty sure, isn't it? 1/3? Well, 1/3 would be 7 over 21, and no. So 1/3 is not going to work, so I can go to 1/4. Now, is 1/4 less than this? Well, yes, because 1/4 of something in 20s would be, what, 5 of them? And 5 would be less than 7, so I'm good to go. 4 minus 1 is 3, and there's my third. My third is actually greater than. So now what do? I take 7/20 and I subtract the 1 over the n. And when I do this, I get a common denominator of 20. And so I'm going to multiply by 5. And I get 2/20. I now know how to write 17 over 20. 17 over 20 is actually 1/2 plus 1/4 plus this piece right here, which in numerical analysis is called the residual. It's the bit that's left over. And the reason I'm not doing anything with it is because 2 over 20 will simplify to a unit fraction, and lo and behold, it takes 3 unit fractions to represent 17 out of 20. And there's the answer. And this is Fibonacci's methodology. I encourage you to look at why it works in your textbook and be able to utilize this method. It's very ingenious. I hope this helps.